as I think it's standing at the fundamentals before getting our teeth into aerodynamic effects and tricks. So, in this video, that's what we're going to do. We're going to look at the building blocks of aerodynamics. A lot of it will at first seem removed from directly what you hear about, what's happening across the wings and body of an F1 car, but these fundamental aspects will soon bring us neatly back to racing aerodynamics. We're discussing how we can affect the way air moves around. So, we're going to look at pressure, what it is, how it moves around, and how it creates forces. We're also going to look at a key law of physical forces, and we're going to look at airflow. This video will set you up for everything we're going to look at aero-wise. So yes, it's a little bit of a physics lesson, but I brought a balloon, so it's fun. Stick with it and we'll wind our way back towards F1 as we head towards the end of the video. Pressure then, air pressure. What is it? You've probably got an intuitive sense of what air pressure is, but I'm going to explain it in terms of what's actually going on, so hopefully you can visualize it and understand it more fully. Air is made up of lots and lots of molecules all flying around inside the space the air occupies. We can think of pressure as kind of the busyness of all the molecules present in a particular volume of air. Pressure is basically the total momentum of all the little molecules flying around. To imagine this more clearly, let's think of a balloon. If we fill the balloon with air, the pressure of the air inside keeps the balloon inflated. Now, why is that? Well, all the particles in the air are flinging about all over the place, and naturally they bang against the skin of the balloon. Every time a particle hits the edge of the balloon, it pushes against it with some force. Now, multiply this force by all the millions and millions of molecules colliding against the skin constantly, and you can see it's enough to hold the balloon inflated. There are three main qualities that contribute to just how much pressure there is. One is how many molecules there actually are flying about the place. More molecules mean the air is much more busy, and in the balloon's case, there are much more collisions. We also have to think about how much space the molecules have to move around in. The air needed to hold a balloon inflated will certainly not work on something the size of a blimp. The number of molecules per volume is key here. We're asking how densely packed the air is. Thirdly, pressure is affected by the temperature of the air. Temperature actually refers to how much energy each particle in the air has. Higher temperatures mean the particles are more energetic and they're flying around faster. In our balloon, this means they'll be slamming against the inside with more force in every collision if the air inside is hotter. Aha! So you say, but there's also air on the outside of the balloon with all of its particles banging against the outside. Why don't these particles push the balloon inwards, deflating it? And the answer, of course, is that the air inside the balloon must be higher pressure than the outside. The forces pushing the balloon outward overpower the forces pushing the balloon inward. If the forces inside are significantly greater, the balloon inflates. And now we're starting to see how forces can be generated when air is at different pressures. Now, let's talk about what happens when we open the neck of the balloon. All the air rushes out, right? Now, bearing in mind what we just discussed, it's easy to see why this happens. The air pressure inside the balloon is stronger, so the air forcing itself out of the balloon is stronger than the air trying to force itself into the balloon. The result, the air rushes out. In fact, the air rushes out really fast because it's forced through a tight gap. The principle of airflow, described by the Venturi effect, notes that the smaller a region you force air to flow through, the faster the air will flow. Because you're still trying to push the same amount of molecules through, you've just got less space to do it, so it has to go faster. That's why squeezing the end of a hose makes all the water squirt out faster. You're forcing it through a tight space. As a very quick aside, in the balloon case, there's an extra element at play here. The balloon is elastic, so there is also a natural tendency for the stretchy skin of the balloon to want to deflate. But even if the air wasn't in a balloon, but in something more robust like a can, if we opened a hole between the high pressure inside and the low pressure outside, the air would still rush out. In fact, I just described how aerosol cans worked. So now we've understood how air flows from high pressure areas to low pressure areas, if there's a space for it to flow through. In fact, we've just described air movement, and air movement is aerodynamics. Moving air deliberately is all about creating differences in pressure. If we want to blow out a candle, you create a sudden high pressure area inside your mouth, which rushes out through the small gap you make in your pursed lips to the low pressure outside of your mouth. The result, fast, controlled airflow. Congratulations, you're an aerodynamicist. And now before we move on, I'm going to make sure we're all aboard with Newton's third law of motion. Now, some of you will know what this is already. If not, it's very simple. It's the one that goes, every action has an equal and opposite reaction. But what does this mean in the real world? It means if you push against something, it pushes back with equal measure. If I shove a sumo wrestler, I get pushed backwards. If a car crashes into a barrier, the barrier pushes onto the car and sends it ricocheting back onto the track. If a bird pushes its wings down on the air pushes back on the bird, causing it to stay in the air instead of falling. Inside the balloon, the particle pushed against the balloon skin, pushing it outwards, and the balloon skin pushed back on the particle, sending it bouncing inwards. Now this may seem obvious, you may be saying. Why haven't I seen an F1 car yet in this video? You might be asking. Okay, so here we go. Here's the F1 car. Let's think about what the rear wing does. The rear wing's job is to force air upwards. But if the wing forces air upwards, there must be an equal and opposite reaction, right? When the wing forces air upwards, the air forces the wing downwards, and that's where downforce comes from. It's really that simple. Shove a load of air upwards, and the air will shove you down. Okay, but how are we shoving the air upwards? How does the wing achieve this? Now let's bring this all together. The wing profile is shaped a bit like this. Obviously in real life it's in 3 dimensions and doing all sorts of clever things, but in simple terms it looks like this from the side. Now, at high speeds, in an ideal world, the air is going to come rushing at it in pretty much a homogeneous straight line. In fact, we can think of it as these nice layers of air. When the air hits the wing, some of it flows over the wing. These layers of air will scoot along following the curved surface of the top of the wing and exit out of the back. The rest of the air that hits the wing will go underneath the wing. This air has to take a much more aggressive approach to get under the wing, and you'll see here it gets squeezed between the wing and the wall of fast-moving air below. And as we discussed, squeezing air into a tighter space makes it go faster, so this air accelerates and travels under the wing at a much higher speed, following the curve of the wing and exiting at the back tip. So 2 things are happening here. 1, the air under the wing is going much faster than the air over the wing. This means that the air under the wing is at a lower pressure. Why? Well, let's imagine the particles again for a second. When the air is accelerated through the squeeze, the particles separate out, much like a concertina effect you'll see with a train of cars leaving a slow corner. The faster moving air is more spread out, and as we covered, having less air in a space means the air has lower pressure. So, with low pressure under the wing and high pressure over the wing, we know